Hello everyone, Philip here. This video is called Butterfly CFD Toy Plane Part 2. But before we jump in, a quick announcement. I introduce memberships. As you can see here, there is a button, it's called Join, and if you click here, you can join my channel as a member. Within the first level of memberships, the gecko. Now you ask probably why gecko? I thought the gecko is an absolutely cool and incredible creature and deserves also a spot within the Rhino animal kingdom. And that's why I introduced the gecko as a first level of memberships to my channel, with probably more levels within the lizard family. But yeah, we start with gecko. For $3.99 you can join my channel, you can always resign. You get these incredible loyalty badges and they change over time the longer you're a member. And in case of live streams, I also designed some emojis, gecko emojis, of course. Okay, that out of the way, what else do you get as a member? First of all, I will of course announce every new member, and if you want, I can also promote your channel. Membership shoutouts or member shoutouts if you have comments and on videos or in the live chat. Of course, you also get a shout out. And then last but not least, and this is the most important because it gives you some sort of leverage or say on what this channel will produce, and I will listen very carefully on what my members have to say and will build my channel around that as much as I can. Of course, I want to and I will introduce new things to the channel, but members, the questions and comments from members will be prioritized, and I will listen very closely and carefully and try to build my videos around that. I don't have any members yet. It's very new. Be the first one. Without further ado, now we jump into our toy model CFD analysis. As you can remember, and please, if you didn't watch the first video, I highly recommend, otherwise you have no clue what I'm talking here. Very quick review. We have this mesh model. It can be a mesh model, it can be a NURBS model. It doesn't matter really. Important is that when we're creating the butterfly geometry, you can plug in both. You can plug in meshes and NURBS, and they will be translated to meshes anyway, so it doesn't matter. Then we created the wind tunnel, and the wind tunnel is the wind. So we controlled, we talked about the direction of the wind, and we also talked about how we can control the size of the wind tunnel to make it slightly smaller, for example, or bigger. We introduced what type of landscape, what kind of context this model is in, and then we created the block mesh. The block mesh divides the space into smaller cells, which we then apply a grading to. The grading allows for smaller cells towards or at the model and bigger cells further away from the model. We also visualized it to see how that looks like, and then we introduced the Snappy Hex Mesh. And the Snappy Hex Mesh is important. It introduces the model into that block mesh system, trying to approximate as much as possible that shape of that model. We also talked about the global refinement levels, where you can fine-tune your model. If your model is very simple, then this doesn't need to be so high. If it's more complex, as for example mine, then if you have like windows here and stuff, then you introduce higher numbers. The higher the number, the finer the mesh. It works like a multiplier basically. I went back now to 2, 2 and 2, which is the minimum and maximum of the refinement levels, just because we want to introduce the solver or the solution, and for that it's better we start with a smaller number. So otherwise, every time it recalculates, it doesn't take an hour or two to calculate. So it goes quicker. We could go even lower just for now. For that, maybe we do that actually. Let's see. It creates a really ugly mesh, but in order to calculate, or in order to set up the solution, I think it's actually a good thing to do. It calculates the Snappy Hex Mesh very quickly, but if I show you now the output, you see why. I can show you this here. Yeah, it's not very accurate, as you can see. There's a lot of problems here. But in order to set up the whole script and the solution, it's perfect. And then later on, we can go back and refine the model again. So next thing we need to introduce is the solution. The solution is here. We have the mesh turbulence we talk about in a minute, and also the recipe we're talking about in a minute. I don't know why they haven't set it up step by step. It's a bit weird because actually you need the solution first. Butterfly solution. Now that is the tool which very much then interacts with the OpenFOAM software in the background. That's why you need to run your Rhino in admin mode, otherwise it doesn't really work. And what that tool does, it runs, but it also writes this whole calculation into a file, in an OpenFOAM file, including the case, the model, and everything, which we then in the next video probably, or in the next 2 videos, we will look into a bit more closer. We look at the file, the output of that solution a bit more, because we can also look at that file in the ParaView, which comes with the Blue Core CFD installation, which is a standalone CFD analysis tool. Not just fluid dynamics, actually. Can do a lot of other things. But before I talk too much, let's just build this script. So we need to introduce the case. Again, underscore means mandatory input. See, here we need to provide a recipe, and then there's no underscore here. That means it's optional. If there's an underscore on both sides, it means it's mandatory, but it already has a default value. That's what it means. It's funny that run is not here as mandatory. That's interesting because without running it, I don't really understand why there won't be anything. But yeah, they either they forgot it or they have another thought process behind. In any case, we need the run and we need the write, and we can take this from here. You could also introduce just one button. I like to have 2. Okay, let's first, before we run, let's talk about the recipe. There are 2 recipes. There are 2 general recipes. One is the heat transfer recipe and one is the steady incompressible recipe. That's what we need for wind dynamics. And here you have again other inputs. And what we can talk about is, for example, the turbulence properties. Turbulence properties are here, number 4, and you can introduce different turbulent models. And it has also a YouTube here. If you see here, if you hover over these, you can actually see that there are links, CFD Direct OpenFOAM User Guide Turbulences, and I highly recommend to check these out. This video is too short to talk about it. Check it out, read through, watch the video, so you have a basic understanding of these different turbulent models. I'm just choosing this one, and you can still here provide names for the very specific type of the ERA-S model. It's the Reynolds average simulation turbulence model. Again, check the video and read through so you have a better understanding. We need to provide the recipe here, and then we can actually already run the script, run the solution, let's say. You can see it starts to run the solution. And then we have a time. Time means the iteration. It also feels like that it stops every second iteration and writes. That's when it actually writes the stuff into a file. So somewhere on your folder is a file which just receives what is calculated here. We can look at that actually. I'm gonna add a panel port, and now it says running, and I can stop that, and now it's stopped, and you will see, okay, there's a lot of, it has this header saying OpenFOAM, field operation and manipulation, is foam, OpenFOAM, the open source CFD toolbox. And then there's more, there's what build it is, what was executed, the simple form, the time, for example, the desktop name, and then also where this file is. Toyplane case 4. This is Toyplane case 4, and I will talk about this very quickly. So every time I run that, it will continue writing in the same file. So if I continue here, it actually continues from time 126. It just continues from there. Something to note, if you want to restart from scratch, there is a reset tool which can actually reset the whole purge. Here is this one, butterfly purge case. So with that, you can reset, or supposed to be able to reset your case, You can reset the block mesh, Snappy Hex Mesh, the result, and the post-processing. The problem is it doesn't work. I tried it, it doesn't work for me. Either I do something wrong or it's just faulty. There's another way to do it. You can actually, if you change the name here, then it will create a new folder, a new file, and it will restart everything. And sometimes for me, that's the best way to do it. So you saw it's restarting everything, and I'll just turn it off now for now. So because we want to continue and understand why we run a solution, but actually we don't see anything in Rhino. We only see the calculation done running in the background. Well, again, so it writes a file onto your computer, and that file, the form file, can be then used to open in PowerView, which is the tool that's coming with your installation. The open form installation. Now, if you want to see things in Rhino, we need to introduce a bit more. First of all, we need solution parameters. Solution parameters are here, and it always sounds very fancy and confusing, but it's actually not that much, because it says solution parameters. Now I open the solution parameters, I see, okay, there's a control dictionary, there's probes, so I can just join this here. Now, if this would be on true, it will restart the calculation. That's why I turned it off. Every time when you add something, it restarts the stuff. Now we can look at the control dictionary. What is the control dictionary? What does it do? And dictionary for me, I think it comes from the Python syntax. For me, it's more like settings. I would call it settings. Or options. Here, what you can see here is there's a start time and there's an end time and the write interval. These are the three main components here. And you can also purge or write compression. Let's deal with the first three things. We can set the start time. There's already one set, it's 0, and then there's an end time, it's set to 1000. That's basically the iterations. The amount of iterations, and we could set that to a different number, let's say 100, or maybe 100 is a bit little, let's say 300. So then the end time would be 300 and not 1000. So here we can basically control a bit on how long we want to run this thing. And then we have the write interval. That's the interval and how often, after how many time steps, it writes the calculation into your file. I would put it to 2 or maybe 10. If we run that now, it's restarted, and now you can see that every 10th time, after every 10th time interval, it stops. 60, 70, and it will go until 300. What else do we have here? We have probe points. So probe points, imagine that you want to make the wind speed visible on a certain spot within your wind tunnel. Then you set a probe into the space where you want to measure, and then you can have an output, for example, the wind speed, meter per second, or the direction. Or in that, what we also could measure is the pressure, the wind pressure, or the air pressure. So how do we do that? We first need to introduce probes. Butterfly probes, that's what we need. We need that for the solution. Right, so butterfly probes, we can put this in here. Now it's try to restart again, turn this off. Now again we have inputs, points, fields, and write interval. I'm not dealing with the write interval because we already have a write interval here. It's a bit too much, different write intervals, just confusing. So I will just keep whatever is here in the default. And now we could introduce points or a point. So I could have a point somewhere. I'm gonna turn this off so it's a bit more comfortable to look at. So let's, for example, have a point here after the wing. That's my probe, and I can just introduce that here as a point, plug this in here, and here I need to provide fields, and fields define what we actually want to measure. So for example, you can see here a list of fields such as U, P, K, and the default is U and P. So that would be also here, but we could also just say U, just as an example. U is measuring the velocity, the speed of the wind speed. And P would be pressure, Pascal. So we have this, we have that. Now we're getting closer. If I turn this back on, now I have some issues here. I would just recreate that. Seems like it's the only way now. Okay, it's running again. And it goes through, see, 47 already, 55. It just goes until 300. And you can change things during the calculation even. Now the problem is we still don't see anything. What we could do now is get the solution, we can load the probe points. Wait, so we go back here, butterfly, we load the probes. Oh, sorry, the butterfly load probe value. That's what we need. For that we plug in the solution, and we need to show which field we are testing. It's the same here. And now we see, there's a value in there. So if I add a panel, we can see, okay, there is a value in here, a vector. Time is already at 300, it was very quick. And that was the final value. And it's a vector, basically. So if we now introduce vector display and vector, so we can basically add the value here. We could also introduce first a vector if we want. Put this here, then here, makes it more clear. And we need to provide the start point of the vector, which is our probe. I'm gonna introduce a relay because I like relays. And we see, okay. Now we have a vector behind the wing. The wind comes from that direction, and it has a certain direction already. So that's, yeah, done, finish. Now you think, wow, this is a very long vector. But to better understand this, we can measure the length of the vector, vector length. It says 8.5. 8.5. That somehow correlates with the wind speed 20. If you imagine that the wind goes behind the wing, it will slow down at just behind the wing, and seems correct that this is 8.5. We could now introduce a multiplier just to control the size, to scale the size of the vector. So we could do this, and then no, wait. We need the amplitude of the vector. That's what we need to do. So we need to control the amplitude. We can place here the vector, and then we can use the vector length to multiply with, let's say, 0.1. Now plug this in here. 0.1. We can also add, of course, a slider, and to go even smaller. Maybe we only want to see vector which is this long. Yeah, I hope it's clear. It's too small. But that's gonna be right, especially when we then introduce more vectors. So that would be the first way to visualize a probe, or the value of the solution at the probe's location. Now we don't have to just use one point. We can introduce more points. We can place them manually. A nicer way is, of course, to do that more elegant by introducing a plane or a box. So you can place points in 3D space, but also in a plane, for example. I prefer the plane, or you could set, for example, several planes next to each other. It's all possible. Let's make it simple first, and we introduce a plane. I already created a plane in the past. Here, it's just a simple surface, and you could create a grid on that surface to introduce these points, or what I like to do also, which is quite nice, is to populate 2D or 3D spaces. That's pretty cool. So I will do that, and I will just take the surface, add the surface here, and populate it with this tool here, populate 2D. And then I can always increase the number to, let's say, 1,000 or even more, 3,000. And these are my points, so I could put them here. And then, of course, I was supposed to recalculate stuff. Now this is a problem because, again, we're introducing something else. It doesn't want to recalculate. Again, the best way for me is here just to provide a new number. And now you can see it starts to calculate. I want to turn off the points maybe here, also the surface. And it also writes now every time. It looks a bit strange now because it calculates and it tries to also visualize it here. Where we see it will stop now at 300 and we see the final result. And probably, of course, the more accurate you want it, the more iterations you should get. 300, that was the final. You can see here the wind speed is much less in the back. It's still a bit big, so maybe we can try this. But yeah, I think we get already some idea on how we can visualize these vectors around the plane. And now, before we conclude this video, I want to also show you that the problem now is that we also have points inside the space, and actually we want to avoid that. We want to not have that even in the calculation. So what we can do, or maybe let's keep it on so we actually see what's happening. We can use the cull function by introducing a cull pattern. So we use this tool here, which can filter a list by introducing a pattern of 0 and 1 or false and true. Now if I put this in here, you can see it's just half, before and after. This is because it introduces a pattern which is false, false, true, true. In order to change the pattern in our favor, let's get another tool, which is the inside. Yeah, in our case, we need to use this one, mesh inclusion. If you use B-wraps, then you can use this one here. Point in B-wrap, it does the same thing. So either this one or that one, depending on what your model is. In our case, in my case, because it's a mesh, I use this mesh inclusion tool. So I load the mesh in here, and then I measure which points are inside and which are outside. And that creates a pattern of false and true, checking each point, say, oh, point 1 is outside, it's false. Point 2 is outside, it's false, and so on. And then some of these points are inside, and then it's true. And that creates the pattern. If I put this in here, I actually get a very funny shape of my plane. Now I would need to find a way to invert that. Can use that invert boolean, and I get the inverse. Now I changed that interval again because it was nicer to see it more often. Change the writing interval to 2, just for me to see it better when it's actually calculating. And we can rerun that whole thing. But before, let's clean up a bit. So this is the probes, and here we have the solution. We can add this here just in case we need it, and then visualization. Visualization. All right. Okay, so let's rerun it. By the way, it always creates new files on your computer, so at some point you want to go into the folder and clean it out, especially if you have a laptop with limited space. So I'm recreating the hex mesh and the block mesh, and I think maybe this time we crank it up a bit, just to make it a bit more accurate. So we might see also difference here. Let's do this. Takes a bit longer, but here in the video you don't need to wait because I just cut it out. Turning on the plane because it's nicer. I cannot get rid of this point, by the way. And now final rerun, write and rerun. We maybe add a bit more here, 500. Hoppla. Okay. Is it not cute? All right, finish. The next time we look into a more colored version of these probes to color the speed, you know, give different speed a different color. We might also look into how we could visualize the pressure, the air pressure on plane or the surface with the ladybug heat map option, and then we also might look into residuals. Very interesting topic, residuals, butterfly plot residuals. It's basically trying to measure the accuracy of your solution or the calculation, or more like visualizing it so you can see if your solution is actually successful or not. That tool is also a bit buggy. I think it sometimes works and sometimes doesn't, and I don't know why. And then in the follow-up video we will look into how this OpenFOAM file actually looks like in ParaView, where you can look at way more things than just some fancy vectors. Alright, I hope you enjoyed it. Please drop me a line if you have questions about the membership. Also ask me whatever you want to ask. And yeah, hope I can hope you see you next time. As a member or not, doesn't matter. It's up to you.